Next we talk about product of vectors. We have already talked about addition and subtraction. We have seen that vectors follow their own algebra, right? So similarly, when we talk about product of vectors, we shall learn that there is a special type of product that we study in vectors. In fact, there are two distinct type of vector products, product between vectors. One of them is called a dot product, which is also named as scalar product, for the reason behind which we shall understand as we study this in detail. The other type of vector product is called a cross product. Also we call it vector product. Okay. So, these are two distinct type of product between vectors that we are going to study. We shall start with the first one, that is the dot product. We say that dot product by definition is defined as A dot B. Please notice the dot that we have used between the vectors to denote the dot product. We will only use a dot when we are talking about dot product. By definition, dot product is A B cos theta. Now, I hope you all understand what is the meaning of the expression on the right hand side. A here is nothing but the magnitude of vector A, B is the magnitude of vector B, and theta here is the angle between the vectors A and B. So, if there is this vector A and a vector B, and both of them make an angle of theta with each other, then it is this theta that we are supposed to use to find out the dot product. Okay. So, as we define dot product using this expression, we can look for some special cases here. See that if the angle between the two vectors, if theta takes a value of 0 degrees, in that case cos theta, cos 0 will take its maximum value, which is 1, and the dot product A dot B in that case will be equal to just A into B, because cos theta will be 1. So, understand that AB is the maximum value that the dot product of vectors A and B can take, right, the magnitude of product of the magnitude of the two vectors. In case if the angle between the two vectors theta is 180 degrees, which is when the two vectors are pointing in opposite direction to each other, in that case cos theta, we know that cos 180 degrees is the maximum negative value that cos theta takes, which is -1, and in that case the dot product of the vectors A and B will also take its maximum negative value, minus of AB, which is the maximum negative value, right. That is when the two vectors are pointing opposite to each other. What if theta is 90 degrees? What does theta being 90 degree imply? This means that the two vectors are perpendicular to each other. See that when the two vectors are perpendicular, cos 90 is 0, which implies the dot product of two vectors will be 0. A dot B is 0, which is a special case. In fact, we use this special condition to check whether two vectors are perpendicular to each other or not. So, we say that if the dot product of two vectors comes out to be 0, we can say that this means that the vectors A and B are perpendicular to each other. Vector A is perpendicular to vector B. This is a special result that we use to find out the condition of perpendicularity, the norm, the two vectors being normal to each other, perpendicular to each other. Then we can have some general cases. For example, if theta is less than 90 degrees, that means theta is an acute angle. If theta is acute, in that case we know that cos theta takes positive values. Cos theta is positive in the first quadrant, which means that the dot product of two vectors will take positive values, right. A dot B will be positive. On the other hand, if the angle between two vectors is greater than 90 degrees, which is obtuse, in that case, since cos theta takes negative values, cos theta is negative, which implies that the dot product of two vectors making an obtuse angle with each other will take negative values, isn't it? So, these are some special cases that we can know. Now, as we look at the expression for the defining expression for dot product, do you see that as we try to write the dot product A dot B as A B cos theta, all the terms on the right hand side are scalars. These are magnitudes. Magnitude of vector A into magnitude of vector B into cos of an angle, which will also just be a magnitude, right, just a number. So, as we look at the expression on the right hand side, we understand that everything on the right hand side is a scalar, and since we are taking their product, the product will also be a scalar. That's the reason why dot product is also called a scalar product. Why? Because the result that we get out of a dot product is a scalar quantity. It is not a vector. Though we are taking the product of two vectors, the answer that we are getting is a scalar quantity. Hence the name scalar product. We can talk about some examples of dot product. One of the most important example of dot product is work done. Work done by a force W, which is defined as Fs cos theta, as no, some of you might have studied already. See that force is a vector here, S here is the displacement vector, and theta that we take up in this formula is the angle between the force and the displacement. So, see that this is nothing but F dot S, the dot product of the force vector with the displacement vector. So, work done by a force is actually the dot product of the force vector with the displacement vector. Similarly, we have power delivered by a force, which by definition is the work done per unit time, and in terms of dot product it is defined as F dot V, the dot product of force vector with the velocity vector. This is also a scalar quantity and an example of dot product. Now, the next thing that we can do is we can try and find out the value of dot product of a vector of two vectors when the vectors are given in their rectangular component form. Rectangular component form means dot product of vectors given in their rectangular component form. What does that mean? That means that we have been given vector A as AXI cap plus AYJ cap plus AZK cap, which is the rectangular component form of vector A, and vector B is given as BXI cap plus BYJ cap plus BZK cap. So, as the two vectors are given in their rectangular component form, we are asked to find out the value of A dot B. How do we do this? We can't directly use the above definition that we have talked about. The definition A dot B is AB cos theta is not directly applicable here, because though we can find out the magnitudes of the vectors A and B from these two expressions, we cannot get the angle between them just like that. So, there is another way, in fact it is a small derivation that helps us find out another formula for dot product of vectors when the two vectors are given in this form, in their rectangular component form. Before we go on to that definition, we will first talk about dot product between unit vectors along the x, y and the z axis. For example, what is the value of I cap dot I cap? Let us see that. From the definition that we have given for dot product A dot B is equal to AB cos theta, understand that I cap dot I cap will be mod of I cap into mod of I cap into cos of the angle between I cap and I cap. Now, I cap and I cap both are equal vectors, they are the same vectors, both of which point along the x axis. So, the angle between them is 0 degrees, they are parallel vectors, they are actually equal vectors, and since these are unit vectors, their magnitudes will be 1 each. So, what are we getting here? Mod of I cap is 1 into mod of another I cap is also 1 into cos of 0, which is also 1. See that the dot product of I cap and I cap is coming out to be 1. And we understand that same values will be there for j cap dot j cap as well as k cap for k dot k cap, right. Now, let us look for the next set of dot products, which will be I cap dot j cap. What do you think will be the value of I cap dot j cap? By definition, this should be I cap, the mod of I cap, which is 1, into the magnitude of j cap, which is also 1 because j cap is also a unit vector, into the cos of the angle between I cap and j cap. Now, I cap is a unit vector pointing along the x axis, whereas j cap is a unit vector pointing along the y axis. Since x and y axis are perpendicular to each other, we understand that I cap and j cap are also perpendicular. So, the angle between them is 90 and cos 90 is 0. So, I cap dot j cap will be 0. Do we understand that the same value will be there for all the other dot product pairs that we will take between two different unit vectors, which means j cap dot k cap will also be 0 because j cap and k cap are two perpendicular unit vectors. K cap dot I cap will also be 0 because a k cap and I cap are also two perpendicular vectors, right. So, once we have known the values of these unit vectors, their dot products, now we can go about finding the dot product of vector A and B using the basic definition. So, A dot B, when we write, we have the vector A, which is given as Ax I cap plus Ay j cap plus Az k cap, and we are taking its dot product with vector B, which is Bx I cap plus By j cap plus Bz k cap. Now, what we are going to do is, since this is a product that we are trying to do and we have a term containing we have an expression containing 3 terms here in the bracket and 3 terms here in the bracket, which are in addition with each other, we will try to use the distributive law in multiplication. So, what we will do is, we will take the first term of the first expression, which is Ax I cap, and take its dot product with the first term of the second expression, then the dot product of first term of the first expression with the second term of the second expression, and then the same thing we will do for the third expression of the second expression, third term, and then the same thing we will do with the other terms also. So, it will go like this kind of distributive multiplication that we do in algebra as well, and the same thing we will do with the third term also of the first expression. So, see what do we get here. When we take the dot product of Ax I cap with Bx I cap, we will get Ax I cap dot Bx I cap, right, plus the first term of the first expression Ax I cap dotted with the second term of the second expression By j cap plus first term of the first expression Ax I cap dotted with the third term of the second expression Bz k cap, right. So, this will be the first 3 terms that we will get. Then the next set of 3 terms will be when we multiply the second term of the first expression with all the 3 terms of the second expression. So, Ay j cap dot Bx I cap plus Ay j cap dot By j cap plus Ay j cap dot Bz k cap. So, this is the second set of products that we will get. And now, the third set, when we take Az k cap and take the dot product of that with all the 3 terms on the right hand side. So, Az k cap dot Bx I cap plus Az k cap dot By j cap plus Az k cap dot bz k cap. So these are the 9 terms in total that we have obtained by doing the distributive product of the various terms that we have. Now we need to find out the value of each of these 9 terms one by one. So let us start with the first term. The first term contains ax and bx as 2 values. These are just 2 numbers, right? The components of the vectors a and b along their x axis. And the vectors that we have here are this I cap and this I cap. So we are essentially trying to do I cap dot I cap here. And we know that the value of I cap dot I cap is 1, right? So what we are getting here from the first term is ax and bx, which I can write just like that because these are just numbers, and I cap dot I cap we have just now obtained, it is 1, right? Plus the second term, ax and by are just numbers, ax and by are just numbers, and then I cap dot j cap, which we know is 0 because I cap and j cap are perpendicular to each other, so 0. So the second term goes to 0 because it contains dot product of 2 mutually perpendicular vectors, plus the third term ax bz into I cap dot k cap, which will also be 0. I cap and k cap are also perpendicular vectors, so this term will also go to 0 because of that. And likewise you can see carefully that the fourth term j cap dot I cap will also be 0 because these two are also perpendicular. J cap dot j cap is 1. So here we will have some value. So the next term is coming out to be 0, plus the next term to that will be ay by into 1, plus see that the term next to that j cap dot k cap will again be 0 because j cap and k cap are perpendicular to each other. So this term will also go to 0. The term next to that k cap dot I cap will also be 0. So this will also be 0, plus the term next to that k cap dot j cap will also be 0. So here we have a 0, plus k cap dot k cap is 1. So we will be left with az bz into 1. See carefully that we are just left with 3 terms from the whole expression here. These are ax bx plus ay by plus az bz, and this is what we are getting as the value of a dot b. So this becomes our new formula, another formula rather, for the dot product of 2 vectors when the 2 vectors are given in their rectangular component form. In the next video we shall look at the applications of dot product.